I'm just trying to kind of hit on some points of why I've come to some conclusions of through gravity to magnetism to energy to this to that. I mean, I'm going to be missing a lot here and all this because I'm trying to make this just quick to get an understanding where I'm coming from on some of this and to kind of embed it a little better possibly. Anyway, once you get past what I haven't got it all figured out or talked to you or whatever about it, the OM particles into good vibration particles, then you start getting protons and mass. I think the dielectric, even to elemental atoms, is pretty much centripetal. It may have a rotation to it, it may have a swirl, vortex, but it's basically centripetal to the atom, to the element. And it does the same thing to molecules. They try and pull centrally together. And then when you start compiling things, you get more and more centripetal action that's obvious. My point is, I want to talk about, get that to gravity. Once you get enough mass together, whatever the elemental composition is, like this ball, steel ball, solid steel ball, hollow steel ball, solid, this one's solid, this one's hollow, just hear me out, steel bar, it's in planets, whatever you want to talk about, and we'll get into a magnetic core inside a planet. You're going to have dual this. What I'm going to say is each of these have their own frequency or their own speed of focus of the dielectric centripedially doing centripetal penetration, spherically radial, terminating at the core. It's passed in atom to atom to atom to terminate at the core. When that gets situated for the size of the mass and the elemental composition of the mass, that is the gravitational property of the mass. Take two of these out in space, and you're going to, see what that happens. Here on Earth, I know what the centripetal speed of the dielectric going into the Earth is the terminal velocity of Earth. That's it. It's pulling that down. This is caught in that flow as it steals its own electron functions to the bigger Mother Earth. The table's in between me and the floor. Okay, so anyway, that's the frequency that Mother Earth has to drag these two things at the exact same rate. And you've seen, I don't know if you've seen the video with, maybe I'll throw his name up here, where he went into a vacuum chamber, emptied out all the air, dropped a bowling ball and feathers, and they fell at the same rate to the ground. Without wind resistance or any resistance, the pull of the dielectric into Mother Earth is the same for every piece of mass on it. It doesn't matter. So anyway, everything has its own frequency, and it's centripetal unless it's magnetized or it's experiencing some kind of energy. Radioactivity possibly, or electric current, fission, fusion, any kind of energetic action can displace the centripetal position of the item with dielectric gravity. So everything has its own frequency. That's what I'm trying to get at with here. Everything has its own frequency of dielectric, and if it has a magnetized core, you've got two different frequencies happening simultaneously. The one frequency is the centripetal for the mass that's not magnetized, and if it has a magnetized core, which I say most planets and stars do, you'll have a dual higher frequency magnetic field running at the same time you've got centripetal gravity running. And they interlock, intermesh, like a slip gear. They work with each other to do both simultaneously. So anyway, I want to get that out of the way about how gravity works. It's centripetal. That's the only time the dielectric really is centripetal, is gravitational for atoms, molecules, and then mass that's not experiencing energy or magnetism. Now, I want to move on from that thought that gravity is centripetal to things that's not experiencing mass to why a magnet does what it does. So I want to move on to show you why the north shoots out. I've got more to why that does that. I'm going to move on and do that. Okay, there's my beat up magnet sphere. I'll show you. It's the only thing south, north, magnetized. This is not, it's just a steel ball painted red. Okay, no magnetization. The difference is on gravity, the centripetal meets at the core, so it balances out. You understand? It's flowing in, but it stops when all sides meet at the core. So it's like a once it gets there and comes together, it don't really slam together, might when it fuses or whatever, but it's like a flow, a steady flow. And once it finds it, that's the gravitational property of it because it's centripetal. Magnets are not centripetal, they're linear, like I've said. So when it comes in the south side, there's nothing for it to bang back against, to meet itself. The dielectric can't meet itself at the north hemisphere of this. It can't meet itself there and hold. And I'll show you why, but in a natural gravitational non-magnetized situation, no energy, each place that it's coming in anywhere around this, it's meeting the other side. You got Joe coming in 50% to the middle and Frank coming in all the way around it, centripetal. They're hitting each other in the center to give it balance. That way as it comes in, it stops and it kind of backlashes into the gravitational property. Complete 100% centripetal 360-degree balance. A magnet can't do that, and I'm going to show you why now. It's coming in one side. It's got linear feed coming in. There's no way that the dielectric out here can stop it right at the north hemisphere like it stops itself at the core of a regular sphere. It's not magnetized. It can't do that. There's no way, because then it would be like this half hemisphere. And let me show you. Let's say the half hemisphere is the north side of this magnet, okay? As that comes in the south, if it's supposed to stop right here at this marker on the north hemisphere of this magnet, it's not going to stop there from the pressure coming in out here because you got too much going one way to feed it. It would just push it. It would just push the magnet. Do you understand? Unless this was fluted and the input was fluted, which is what we see. This is kind of fluted with its cone, and this is coned in reverse. It's like an escape valve, a release valve. It has to do that or you're going to wind up with like blowing air into this hemisphere. It's just going to blow it. It's going to move. This magnet's going to travel, and it's going to keep accelerating and picking up speed until the dielectric can't keep up with it anymore, and it's going to turn back into good vibration particles or OM particles. That is why there's a word and a term for this. I've looked and I can't find it, is that when something comes up to a barrier, but yet it has to continue to go through it, it will release valve it and work its way back. That's why you get your flyback. The release valve is that the dielectric says, we got to feed this in one direction, but we can't stop right at the atoms here because there's no way to keep the mass from moving. Now, how do I know that? Because when I drop this ball here on Mother Earth, the dielectric going into Mother Earth on its spherical radial centripetal pulls it. It moves it. And the speed that it will move it is the terminal velocity that this will reach on Mother Earth. If this was in space or even here, and the dielectric tried to stop at the perimeter of the northern hemisphere where the acceleration should be feeding up to that point in a linear way, it would have to push this, just like it pushes either one of these towards Mother Earth. You got me. So it can't stop at the north hemisphere and feed it one direction, linear. It has to let it go on through an over-acceleration to feed the atoms. They take what they need, but the over-acceleration is recycled what it can, and the rest of it is passed on in whatever, it's there, but you only see it when it's something that aligns, something metal. And the point of that is I can use copper in between. The copper allows that to pass through, just like the magnet allows it to pass through, but it takes what it needs. The copper allows it to pass through, but it takes what it needs. This piece of steel allows it to pass through, but it takes what it needs. But it just happens to be ferrite, so it aligns with what the magnet's doing. And we can get deeper into that later, too. But I'm trying to show, at first, in my theory, I thought that the diversion happened right at the mass. The incoming static charge just pushed back against it right at the mass and flipped it over. And you see it does the same thing through wood. The wood just allows the acceleration to happen, doesn't affect it. It's either aligning its domains to a acceleration to meet the magnet, because the magnet will not stay next to that without the steel ball there. So this allows it to go through, and it may align somewhat, but not enough to hold anything. So I think it just goes between the atoms. Same thing with paramagnetic and other semi-magnetic materials. My point was, I used to think that the diversion happened right at the mass. It doesn't. With the Gauss meter and all my experiments, wherever this starts accelerating in, gets up to the highest acceleration of what the Gauss is of this magnet. You have the same acceleration on the exit side, and then it reduces back to 1 or 0, where this one starts at 1 and 0. Positive in, acceleration, negative out, deceleration. So I'm hoping that might get it. That's why a magnet does what it does with the linear penetration. It has to shoot on through. It can't stop right at the mass and feed it like it does centripetal. There's a term and a reason for this, and I can't find it. It has to let it on through like an escape or pressure valve or relief valve. Then it deals with it out here. Where the acceleration started over here, it can deal with it better over here after it's fizzled itself down to whatever the mass called for to be coming in over here, because it's linear instead of centripetal. I'm hoping you get this. I'm hoping you get this. That's why a magnet has the overshot, and the reason that everything lines up the north and the south is where the overshot's acceleration is, or the acceleration is most intense at the core central of the pole, and most intense at the center of the pole, and the diversion happens equally with acceleration being less and less as you get out and away, and less as you get out and away. That's why this ball will not stay at the equatorial plane. It's going to roll to one side or the other. Anyway, I want to get that hopefully pushed down, is why this has the overshot. And we'll move on. Okay, this is just a little rectangular piece of steel. And, I'm going to do an animation showing the same thing, similar. Very similar to this same experiment, demonstration. When the magnet is put up against it, like a magnet on your refrigerator or a magnet to anything, when it's put this way with the south is pulling dielectricity, the dielectric, through the steel into itself. And that acceleration is what holds them together, because it's steel. If this was wood, it wouldn't do that, but it would pull through the wood if I put this behind the wood. Okay, that's why it does that. It's pulling it in that way, going into it. The magnet's drawing it from the piece into itself. And when I flop it northways, the magnet is pushing into the steel. The steel is being fed by the magnet, but it's way more than what it needs in this area, so it disperses it. But the acceleration coming out aligns those domains to where it holds. It's obvious. We see that happening. But it's a reverse operation. The south pulls out of the steel, and the acceleration happens within the steel right there. It's magnetized temporarily. Take that away, and nothing's going to stick to that, right? But it still will, the magnet. Turn around, same thing. It's magnetized reverse, but it works. And nothing's going to stick to this, but it will. This on that side, same thing. The acceleration is so intense there, is why this will not stay in the middle. It wants to go to one end or another, because where the acceleration is highest is where it's going to go to, the positive or the negative. But the acceleration is the same on each end. 10 there, your highest number there and your highest number there. And on a bar, I showed you for it, just less in between. And spheres work it different, but the same principle on the poles. Okay, so I wanted to get that out of the way. I'm going to run a little animation that kind of gives a visual to this. Then I'm going to move on to something even more explanatory of why this does that and how it does it. And we'll move on. Okay, so here's our magnet. It's like a little filing cabinet here. Our south is up against it in this particular situation I'm showing, just kind of giving you a visual what I'm trying to explain here. And it's just sitting there, and it's holding itself there from the acceleration. And I let this go too long, but just give you an idea. The the animation of what it is. It's one bar magnet, but I had to use two pieces to color them different. So anyway, the south is against the cabinet. So the south is pulling the dielectric from the air through the metal towards itself. And the acceleration is what holds them together. That's it. It aligns with it. The steel cabinet aligns with the acceleration. Now here's the north. It's pushing into the cabinet, and the acceleration is why it stays there, and it aligns either direction, coming or going. And that's it. Okay, you saw this earlier. You know, the steel bar and the bar magnet on just a piece of steel, both this way. You saw the animation to it. Now I want to prove it, that that's what's going on, if you will. So I have that, the cylindrical magnet, piece of steel. I have my transformer that I magnetize things with. I have just a little steel bolt here. It's not magnetized. It doesn't stick to anything. And I have, this is what I'm going to use. This is a high carbon piece of steel. It's hardened very hard, and it was an old time magnet. And I have it painted. That I'm going to show you that and explain it in a minute. It's not magnetized right now. I have my pole finder. I have my Gauss meter and my voltmeter, which this should show 2.03, 2.04 there, and 2.1011. It's a little lower today than it was on my last experiments. And I can't guarantee which way this is going to magnetize because I'm using AC current. It's basically a DC thing that does it. It just depends on when I stop the current, which way the AC was going. I've done this before, but I got to do it again to show you. So it's not magnetized. Put my Gauss meter back. No pole. If you see, I'm pushing the button, believe it or not. No pole. So I'll put it on here, and I'll see which way it magnetizes. And I don't know. I'm wrong. I'm south on this end. Let me try it again. See if I can get the south to the south. There we go. South side's blue. North side is red, if you see it. North side's red. I didn't have it completely on there. South side's blue. North side is red. Okay, so we're magnetized. And like I've always said, this was having natural centripetal for what shape it is, gravity going into it prior. Once I magnetized it, now it's going through it in one direction, and I know it's going through it that way because I have south and north. And when you saw what this was, south on that side will be 2.03, 2.04. North on that side will be 210, 211. Oops, 210. Now this is going to be way weaker. 0.35, 0.23, 0.21. That's what I want, because I'm going to show you now why this is what that's doing. Is pulling it out of the steel into the magnet, and the acceleration is what holds it there and pulls it there. And the acceleration is going into the steel from the magnet, and that's what holds it there because the acceleration is going that way. And how I'm going to prove that is I'm going to take this magnet, and I'll take this bolt, and it holds it. And I can shake it, and it won't come off there. All right? It's staying on there pretty good. And this doesn't magnetize nearly as powerful as a neo. It's not neodymium material, and I don't have the power to do it. And this is perfect, though. So the bolt holds on there really good. You see that? Now watch what happens when I do this. I'm going to put the magnet on the steel bar, and it's holding it. But it won't hold the bolt now. It will not hold the bolt. Barely. It falls off. You see that? Barely. And it falls off. Now, if I take it off the steel, It holds on there, and I can't shake it off. Do you see that? And it's magnetized still. I get it on there. South, north, south, north. Okay? I'll do it again. I can't even shake it off there. I mean, I could if I really flung it, but I can shake it, it stays. I can put this on this bigger steel. I can shake it, and it stays. But if I put the bolt on there, it just falls. Unless I get it in just the right place, it'll hold, but I can throw it off with just a little fling. You see that? Not much. Not much. It's the same thing that's going on here, why that holds, but that has more power because it'll pull that in, you know, on the ends, and it won't hold it here. It will not hold the bolt in the middle. It has to go to an end because this has got so much, you know, the neodymium and the amount of DC power, electromagnetic field they hit it with. My point is, it's the same thing. This is on one end, this is pushing into the bolt, keeping it there. On this end, it's pulling in from the bolt, keeping it there. But when I do this, this is sucking up so much of the energy, the acceleration that this bar has, which is low, like I showed you with the Gauss meter. It's sucking up so much of it because it's so big, it no longer has the power to do that. It no longer has the power to hold the bolt like it did. I can turn it different ways. I mean, it holds pretty good, but I can fling it off pretty easy. You know, it just wiggles on there. But if I take that off, put it on there, it holds. So I'm hoping this will show you that that's what's happening. The linear acceleration is what causes that to do that. And I can't do this magnet that way. The problem is, because of the way this magnetizes, I can't do it perfectly. I mean, it won't hardly hold the magnet in on there, but it will hold it sideways easy. But you see how it has poles. North, and it won't even hardly show the south or north because this is sucking it up. Now if I do it here, it'll show a south all the way along, then a north. North, get my finger on it, south, north. When I put it on there, it's sucking so much of the acceleration out of this that it doesn't show poles. Well, there's a little bit of north, and that's it. So I'm hoping that will prove to you that is how magnets work, why they work. There's an overshot. It can't stop right here like I originally thought years ago. It shoots out, decelerating at the same distance with the same power that it's coming in, accelerating. You know, 10 and 10 or full power here. Over here less, over there less, over here less, over there less. It's bulbs, like a quasar. There's bulbs around each end of a bar magnet. So I just wanted to show you that. That's what I got. We'll get some thoughts on this. I just wanted to prove that point of it, that how I know the overshot is what's causing this reverse polarity. 203 on this side, negative or positive, and 210 on that side, negative. 203 positive, 210 negative, 210 negative, if I get it on there, just right, 210, 211, and 203. And we'll move on.